So far we've been looking at statics and now we're going to start on dynamics. So dynamics are when there's a resultant force. So equilibrium, remember, was when there was no resultant force. Now there is a resultant force, so the system's not in equilibrium anymore, and therefore the force is going to cause an acceleration. And Newton's second law, that you'll probably already know from GCSE, is usually written as F equals ma. We saw when we started forces that weight is a type of force, and F equals ma directly links in order for us to calculate weight. So if force is mass multiplied by acceleration, given that weight is a force, every object that exists has a mass, and acceleration due to gravity is g, then we can literally transfer this formula to W equals mg. And in mechanics we use the value of g as 9.8. Okay, so pause the video now, perhaps jot down the example and then we'll work through it together. Just got a little note up here. If the mass is 5 kilograms, rather than actually working out 5 times 9.8 to get the weight, we always leave it in the form 5g right until the very end of the calculation. This is because sometimes you'll find that all of the g's cancel out, so it just makes your life a little bit simpler. Okay, so in example 1, first of all we're asked to work out the weight of a car which has got a mass of 1,230 kilograms. So start by writing out the formula. W equals mg. Mass is 1,230. G is 9.8. So we could write that as 1,230 G, and that's how we'd leave it if we were carrying on with a further calculation. But when we actually work that out, it's going to give us 12,054 newtons. Okay, question B feels like it's going to be pretty straightforward. However, they've thrown us a curveball. This is in grams, whereas the mass needs to be in kilograms. It needs to be in its standard international unit. So that means we've got to convert this into kilograms first before we do the calculation. And we know that there's 1,000 grams in a kilogram, and therefore this mass is 0.00454 G, which is the same as 0.00454 times 9.8. Giving us a weight of 0.0445 newtons, correct to 3 significant figures. Finally, in C, we're given the weight and we're asked to find the mass. So W equals mg. The weight is 3.2, equaling mg. So 3.2 over g is going to give us the mass. And therefore the mass is 0.327 kilograms, correct to 3 significant figures. Right, so example 2 here, we're asked to calculate the acceleration if we've got forces acting on an object of mass 25 kilograms, and here are the 3 forces acting on our object. So we need to start off by finding the resultant force, and then we can put that into the formula F equals ma. Now personally, I like to just substitute all of my forces in instead of F straight away, but if you want to work out the RF first and then sub that in, then that's also okay. So I'm going to say that F equals ma, and all of my forces are 40 I15J plus 20I minus 7J plus 31I 23J, and my mass is 25, and we know that acceleration is going to be a vector because force has been a vector there. We could actually, if we wanted to, have written the original formula in the vector format, underlining them to show that they're vectors. Okay, so we've got 40 plus 20 plus 31, which gives us 91 in the I direction, 15 minus 7 plus 23, which gives us 31 in the J direction. So the final step now to get acceleration by itself would be to divide both sides by 25, which was the mass of the object. And then we can simply write the acceleration as 91 over 25I plus 31 over 25J. Okay, example 3. So we've got a box of mass 5 kilograms resting on a horizontal floor, and like always we're modelling that box, that object, as a particle. So I've shown it as a spherical particle. I'm going to label the mass on as 5 kilograms, and immediately I'm thinking, right, okay, if it's on a surface, I've got a reaction force acting upwards, and I've also got a weight of 5g because it's mass times gravity, acting downwards. Okay, reading back to the question then, we've got a horizontal force of 30 newtons applied to the box, so perfectly horizontal. There we go, we've got 30 newtons. The box is subject to a frictional force of 10 newtons when it's moving. So we know that friction acts to oppose motion. At the moment, all of the motion is going to be in this direction. So therefore, friction has to be acting in the opposite direction. And we are then asked to resolve horizontally and vertically to calculate the normal reaction and the acceleration. Okay, I'm also going to put an acceleration arrow onto my diagram. I can definitely see that I've got a bigger force going to the right to the left, so overall my resultant force is going that way, and therefore my acceleration will be acting that way as well. And we show acceleration with a double arrow. Right, so as we're on to dynamics, we're going to be doing Newton's second law. However, in the vertical direction, this has to be in equilibrium still, otherwise the particle wouldn't be staying in contact with the surface. As soon as there was a resultant force in this direction, either that ball would be flying through the floor or it would be coming off the floor. So vertically, resolving vertically remains the same as with statics. So resolving vertically, upwards we have r, downwards we have 5g, and so therefore that equals 0. And rearranging, r equals 5g, and 5 times 9.8 is 49 newtons. Okay, horizontally now we're going to be doing Newton's second law. And I'm going to pick to the right because that's my direction of acceleration. So the forces in the horizontal direction are going to be 30 minus 10. And then that equals mass 5 times acceleration. 30 minus 10 is 20, so 20 equals 5 times acceleration, which means we've got to divide both sides by 5 to get the acceleration, and therefore the acceleration is 4 meters per second squared. So just a couple of pointers to recap over with this one. Vertically, we have no acceleration, it has to be in equilibrium, so that's the same as with statics, but you see it actually has the same format as F equals ma. It's just because the acceleration in that direction is 0, then mass times acceleration gives us 0 overall. You can see that we're using Newton's second law to the right, and that's because there's a resultant force and therefore there is an acceleration overall. We'll check our units, and one final thing that you might want to do is just to highlight the forces in each direction. So here we've got a horizontal force and a horizontal force, so that's all the horizontals, and then we've got vertical force, and that goes with the verticals. So you might find that a useful trick, especially when the diagrams get more complicated and we start having diagonal forces acting like this.